transportation, transshipment, and assignment problems. Transportation, transshipment, and assignment problems. Now, so in order to keep the class orderly, I would want you to put all your questions and your comments in the comment or text section. I don't want interruptions from the voices and all that, which can make the class quite unconducive. So whatever comment or question if you want to ask a question, you can raise your hand. If you want to have a question, you can put it in the comment section so that we can have an orderly class. Thank you very much for your attention. Now, as the name will imply, if you look at transportation problem, you see that within the world of work, goods and services are moved from one destination to the other using various means. Now, these movements of goods and services come at a cost. So the question then is, how best do we move goods and services from several locations to different destinations or even one destination while keeping cost bearable or very low? And that is what transportation problems are all about. And we can use linear programming to resolve transportation and then transshipment problems. Now, when we talk about transshipment, we are talking about a situation where there is an intermediate point where we transport the goods or services. So for instance, you are moving the goods from the production unit, then first you send to the warehouse. And from the warehouse, you distribute to wholesalers and sometimes to retailers. So there's a transshipment arrangement in this particular problem. Then we also have what we call assignment problem. There are situations where you have to allocate different people to monitor different places. So for instance, if you look at the just ended elections, the Electoral Commission and various political parties had to allocate, deciding how to allocate a number of electoral officers across the country. So how do you assign individuals to various constituencies and even polling stations to ensure that you minimize cost and also minimize the distance traveled by these persons? So that has to do with what we call assignment problems. Assignment problems. And we will take time to look at them and see how we resolve such problems. So what we'll do is that we'll look at the transportation model and use a computer to solve the problem. Then we can look at transshipment problem. After that, we now look at an assignment problem and how we model an assignment issue. So when we talk about transportation, transshipment, and assignment problems, they are part of linear programming problems that we call network flow models. And this tells us that transportation, transshipment, and assignment problems are solved within the framework of linear programming. And indeed, we can use our usual simplex method to deal with such problems. And for this particular lecture, we will focus on how to set up the model mathematically, and then to use the computer, mainly Excel, and then Excel and QM for Windows, to solve such problems. So we'll take our time to see how these are solved. Now, so let's look at the transportation problem. Now, if you look at the transportation problem, the nature of it is that we are transporting a product from, say, different sources to either a single destination or multiple destinations, such that cost is kept at the barest minimum. And in this case, each source that we are taking the product from can only supply a fixed number of units of the product. The same way, the destination where we are supplying the products to demands a fixed number or a fixed unit, fixed number of units of the product, which means that supply sources have fixed unit number of products, the same as demand sources, which also have fixed number of units of the product. So that what we now do in the linear programming framework is that we will have demand constraints as well as supply constraints. Okay? And we can have a balanced transportation problem or an unbalanced transportation problem. In a balanced transportation problem, supply is exactly equal to demand. In an unbalanced transportation problem, demand and supply are not equal. So in the case of a balanced transportation model, all the constraints are equalities. Why? Because demand is equal to supply. However, in the case of the unbalanced model, where supply and demand are not equal, the constraints are, we have some constraints that are inequalities in the model. So take note of that. We can have a balanced transportation problem where demand is equal to supply, or an unbalanced transportation model where supply and demand are not equal, in which case some of the constraints would contain inequalities. So let's look at an example here. So this example looks at a transportation problem where we have wheat that is stored in grain elevators. Okay. So a grain elevator is generally a storage environment. Okay. So we have grain elevator stations in Kansas City, Omaha, and then Des Moines. And each of the elevator stations have their storage capacity or their supply, what we call supply. Kansas City has 150 tons, Omaha 175, and then Des Moines 275. Now, we want to transport these products from the elevator station to mills. So a number of mills, and this is where most of the products will be milled. Okay. So that in this particular case, each of the mills also have the quantities that they demand. In other words, the quantities that they can use. For Chicago, the mill can take 200 tons. For St. Louis, 100, and for Cincinnati, 300. So if you see here, the supply totals 600 tons, which is equal to the demand, which is also 600 tons. So the transportation problem here is, how do we transport these grains of wheat from each of the elevator station to the mills such that cost is kept at the minimum? If you are able to hear me, let me know from the text. Somebody is telling me that they can't hear me. If you can hear me, let me know. Just put that in the text. Because individuals can have, your network can have a problem. So don't conclude that for the whole class. Okay? Please check the network at your side, because from here, my network is very stable. So if you cannot hear, it's more likely to be from your source. So get a reliable internet, and don't make sweeping conclusions that the class is not effective because you cannot hear. Please, let's be a little bit circumspect in how we go. So thank you. So I get this thing that the problem is not from my side. So if you just ensure that you have a stable internet so that we can move together. At the moment, my internet is very stable. Okay, yes. Now, so that is a problem. How do we transport the wheat from the grain elevator stations to the mills such that cost is minimized? Okay. To do that, we will need the cost of transporting from each point the cost of transporting from each point to and here each point to the other. So you need the cost of transporting, for instance, from each grain elevator to each mill. How much will it cost? What will be the unit cost? And that is provided here. So here you will see that from Kansas City, if you want to transport to Chicago, it will cost you $6 and $8 if you are transporting to St. Louis, and $10 if you are transporting to Cincinnati. Okay. So these cost elements can then help you to set up your objective function. It will mean that your objective function will be to minimize cost. So what it means is that all these costs should be kept at a minimum. Okay. So for ease of modeling, you will see that we have illustrated, we have numbered the destinations. So if you look at the grain elevators, we have numbered them 1, 2, 3. Take note of the numbers. So 1 is Kansas City, 2 is Omaha, 3 is Des Moines. If you look at the mills, Chicago is numbered A, St. Louis B, and then Cincinnati C. Now, let's look at the network we are talking about. So if you look at this diagram, at the left side, we have the supply points, and these are the grain elevators. From each grain elevator, we can connect to a mill. So from Des Moines, we can follow this route to Chicago, and this route, oh, the pen is a bit hazy. Let me pick it again. So we can connect to Cincinnati and also connect to St. Louis. The same for Omaha and then Kansas. Each supply point is linked to a demand point. So, but you see that the demand and supply in some may be equal, but each supply point may not equate to each or a specific demand point. And that's why there's a need to determine how you should transport these items so that you can minimize cost and then keep the business running. So let's look at how the model is set up. Okay. Remember, we said that the objective is to minimize cost. So here you have to pay attention very carefully. So we are minimizing cost. So let's get back to the cost diagram. So this is the cost. So if you look at this, so the cost of transporting from Kansas to Chicago is $6. So it means that we have to get a sum of all these costs and multiply by whatever quantities that we are sending to each destination. And sum, that gives us the cost. So for instance, if the cost of transporting from Kansas City to Chicago is $6, so we can say that the quantity of wheat to be transported, X, from Kansas City. So Kansas City, we said, is 1. To Chicago, which we label as what? A. We can use those as the subscript. It will be X1 what? A. X1A. Such that, so X1 A. So that will be describing this cell. So we bring the 6 there. So X1A 6. So come and see, you will see it here. 6 times what? X1A. So that is this. So take note of the 1 is for the subscript 1 is for what? The Kansas City, 2 is for Omaha, and 3 for Des Moines. So we are going to sum X1A. So 6 times X1A plus 8 times what? X1B. St. Louis is B. So it will be what? 8 times what? X1B. Then you come here. It will be 10 times what? X1C. Plus, then you now come X, because this is 2, X2, and this is A. So we are looking for this position, which will be what? X2A, and the value is 7. So 7 times X2A. Then we'll have here 11 times what? X2B. Here will be 11 times X2C. Plus, you come here, you have X3, and this is A. So, and it's 4. So, because Chicago is A, and it's 4. So, 4 times X3A. Here will be 5 times X3B. And this will be what? 12 times what? X3C. Okay. So, that is what you see here as the objective function. Okay, so with the objective function, the respective quantities are multiplied by the cost and sum. So that gives us the objective function. Now let's move to the constraints. Coming back to this figure, now this table, remember that we said that supply is fixed, demand is also fixed. So I'm talking of this one. Supply is fixed, and then demand is also fixed. Now the issue is, how do we ensure that we set up the problem such that we meet demand and supply constraints? What this means is that we must ensure that in our problem formulation, the total amount that can be supplied from Kansas to Chicago, St. Louis, and Cincinnati is equal to 150. So that is a supply constraint. That's the first supply constraint. The total supply from Kansas City to Chicago, St. Louis, and then Cincinnati should be 150 because it cannot exceed 150. The same thing here. The second supply constraint is that the total supply from Omaha to Chicago, St. Louis, and Cincinnati should also be equal to 175. Similarly, the total supply to Chicago, St. Louis, and then Cincinnati from Des Moines should be equal to 275. So that becomes the third supply constraint. So we have three supply constraints that are illustrated here. So that is what you see in the first three constraints. So this one is supply from, we said one is Kansas. So Kansas to Chicago. Chicago is A. Plus supply to St. Louis and then to Cincinnati should be equal to 150. The same goes for the other ones as I illustrated here, previously. So here you just need to take note of the subscripts. The 1, 2, 3 will stand for the elevator stations, and then the ABC will stand for the mills. Okay. So this one will mean that the amount shipped from elevator 2 to mill A plus the amount shipped from elevator 2 to mill B plus the amount shipped from elevator 2 to mill C should be equal to 175, which is what I illustrated here. That's here. Then the third one, the amount shipped from elevator 3 to mill A, from elevator 3 to mill B, from elevator 3 to mill C should be equal to the total supply that elevator 3 can contain. Yeah. So the first three are called supply constraints. And this brings us to the demand constraints. So let's come here. We'll see it. So let me erase. These are the fixed demands that each of the mills can contain. So at Chicago, what we are saying is that the total amount that Chicago can demand from Kansas, from Omaha, and from Des Moines should be equal to 200. And that is this equation. Yeah. Then for St. Louis, the total amount that it can demand from Kansas, from Omaha, and then from Des Moines is equal to 100. So that is this one. And lastly, for Cincinnati, the total amount it can demand from Kansas, from Omaha elevator, and from Des Moines elevator is 300. So it cannot be more than that. And that is the last demand constraint. Okay. So somebody is saying he thought we are dealing with a minimization problem. So why use less than or equal to? So as I indicated from the beginning, if you followed, transportation and transshipment are special type of linear programming problems. So, and that is why we are treating it as a separate topic. They have some unique peculiarities. So we talked about balance or what? Unbalanced transportation problem. So if you are doing an unbalanced problem, then you can use less than or equal to. But if you are dealing with a balanced transportation problem, as we have in this case, then it will be exactly equal to. Okay, so Francis, that's the explanation to your question. Now, then lastly, we have our non-negativity constraint. Okay. So let's look at how we solve this particular problem. Now, if I share this exhibit with you, so you can actually open that up from your end and then get the results. Now let's indicate, let's discuss a bit about the configuration of this particular solution, how we go about this problem. So you will see that because this is a transportation model and we've been provided with the quantities as in demand and supply, as well as the shipping cost, we need to put all of them on the spreadsheet. So here we have listed the grain elevators and then the mills. So the supply is indicated. So if you look at the F column, that is a supply, so the capacity. Now, we can then try to estimate exactly how much has been shipped. So grain shift. So the grain shift will be a sum of these empty cells on the row. So for instance, if you take the one shift from Des Moines, it will be C7 plus D7 plus E7. That will give you the amount that has been shipped from that destination. Then, if you look at the supply as well, if we want to know the grain that has been shipped, if you look at the demand as well, if you want to look at the grain that has been shipped to demand stations, you can sum along the column, the empty cell. So for instance, if you want to know the amount that is shipped to St. Louis, it will be, for instance, D5, which is this, plus D6, plus D7, which will give you this amount. Now, but we are minimizing cost, okay? So take note of how the objective function is set up. We set up the objective function using the sum product function in Excel. Because the cost, if you take your minds back to the minimization problem, so this is what is supposed to be in the cost cell, where we are just multiplying the cost by the quantities and summing. So what we could do really was to multiply this by that, plus multiply this by that, plus multiply this by that, in that order. But that will be a bit tedious. Okay? That is following the formula above. So the sum product command, we can use it to do sum product so that everything here in this area that I'm shading will be multiplied by the respective cost elements that are on the cost table. That's basically our minimization problem. So that is what is the formula that is in the cost cell. Okay? So we can do sum product of what is here, which is this portion, C5 to C7, Then some product K5 to M7, which is what is here. And Excel will automatically multiply each by the other for us. And that gives us the cost minimization cell element. Now, Solomon is asking how we can determine whether the problem is balanced or not. To determine whether you are dealing with a balanced or an unbalanced problem, you just need to sum all the supply sources and also sum all the demand sources. If the demand sources and the total of the demand and the total of the supply are equal, then you are dealing with a balanced transportation problem. If the demand is more than the supply, it's an unbalanced problem. If supply is also greater than demand, then you are dealing with an unbalanced problem. All right. So this is the exhibit 6.1, which I shared with you. So with this, we can just see what is happening by trying to estimate. So we go to data as we usually do, then solver. You click on solver and then you would find that we have already gone about the solution. So we take minimization. The objective function is in C10. So C10, that's the cost. Then changing variable cells, these are the elements in the empty sheet here. So the elements in the empty, sorry. So those are what we are trying to estimate. In other words, what quantities we are to ship. We are to ship to the various demand points. Okay, then the constraints, we have demand and supply constraints. Take note that the constraints are in two sets. We have the supply. So if you look at the solution here, which I have highlighted, you have from G5, that's grain shift should be equal to grain supply. That's under the supply side. So that is what I have highlighted. Okay, so the grain shift column, you select all of them and you equate to the grain supply. You select all the elements there. Then the second constraint is the supply constraint. which is saying that all the elements that are shipped to the demand centers, that's C, and here C9 to E9, should be equal to the quantities that are demanded, which is what? C8 to what? E8. Okay, so those are the constraints. And here, in terms of the solution, we select the simplex LP method. Okay, we use the simplex LP method as a solution, solution model for this particular problem. So from here, we can click solve. And you see that the cell has been populated with the answers. The cells have been populated. Under the cost side, you see that the total cost for transporting the products is 4,525. Just a minute. So that is a cost it will take for us to transport from the elevator stations to the mills. So let's look at the solution carefully. Now, the solution says that transport from Kansas City, transport 25 to Chicago, nothing to St. Louis, and then 125 to Cincinnati. From Omaha, transport nothing to Chicago, transport nothing to St. Louis, transport 175 to what? Cincinnati. From Des Moines, transport 175 to Chicago, 100 to St. Louis, so that the entire 275 is transported. You can also interpret it from the mills and say that Chicago sources 25 from Kansas City and sources 175 from Des Moines to meet its 200 demand. St. Louis receives nothing from Kansas, nothing from Omaha, and everything is gotten from what? So St. Louis gets everything from Des Moines. For Cincinnati, it gets 125 from Kansas City, 175 from Omaha to meet its what? Demand of what? 300. So that is how you interpret this model. And you see that there are no slacks because grain shipped is equal to grain supply and grain demanded for each of them. You see that there are no slacks. Okay. So that is how we can solve a typical transportation problem. Okay. So this is a network diagram showing the solution that I just illustrated, that Kansas City take 25 to Chicago, take 125 to Cincinnati. From Omaha, you take 175 to what? Cincinnati. And then from Des Moines, take 175 to Chicago, and then 100 to what? St. Louis. So that is how this problem is solved. Now, I have also given you exhibit 6.7. So, which is T1 for Windows solution for similar problem. Now, with this, not much will change when it comes to a solution. And it follows the same procedure that we've been doing previously. Okay. Francis, you are asking whether the solution can be the interpretation. You rather interpret solution. The solution itself is not interpretation, but you interpret the solution. Okay. So when you can open exhibit, I think 6.7 and solve it in a similar manner. But remember that here you are dealing with what? Transportation problem. So if you come to your tailor, under tailor, you see transportation and transshipment. So we are dealing with a transportation problem. I want to open the file. So you can open the file directly, or you can also create a new file and enter this data there. Okay. In other words, suppose you are given a problem of this nature, you can enter it in this manner. All you need to do is to go to new. So you come here new, because you are under transportation. So the number of sources here we have 3. The number of destinations is also 3. Then you click OK. This interface will come. Then you enter the data. Enter the demand in the demand side and supply in the supply side. And then the others, you enter the cost. Or if it's distances, you enter them. Okay. But because we have already entered them, I can use this example. So once you load it, you can solve. Okay. So, and Excel, the QM for Windows tells us that there are multiple optional solutions that exist. And you can see it from here. It says that multiple optional solutions exist. In other words, we can have several combinations of shipping these items that would also give us the $4,525 as the cost. So we should take note of that. So long as the solution is 4,525, then we know that it is the least cost of shipping the items. The QM for Windows will give you some other items, including marginal cost, solutions, that will be provided, and so on and so forth. Okay. So just to illustrate to you that indeed we can solve it both using the QM for Windows, among others. Okay, so let's proceed. Okay, so so as much as possible, we'll try to record and then share later, Mohammed. So your concern is noted. For Abubakar, I can go through the process of creating a new one again. So to create a new one, what you just need to do is to, under the module tree, or you come to module or tailor, but where you go by chapter, make sure that you select transportation as the problem. So when you select transportation as the problem, this window will come out, whether new, open, close, etc. So you say new. Then you see that you can give it a title, it's optional. Number of sources. So I can say 3 in this particular case. Then number of destinations is also 3. So I change it to 3. Then the objective here is minimized. So I click OK. This will appear. So I can then now enter values here. So you see here 4, 6, and so on and so forth. You can populate the space here. You can do demand and supply illustrations. Okay. So you can enter values arbitrarily and solve the problem. Okay. So I'm just entering values arbitrarily. Okay. So with this, you can solve the problem. So you see that this problem has been solved. This arbitrary problem, it says that the solution is 3,986. Okay. So that's how you can set up the problem. So when I give you a problem, you can just set it up in this simple manner and solve it. And indeed, at the end of this lecture, I'll give you a group assignment. You see that we don't yet have a group assignment. I'll give you a group assignment so that you can use that to practice on these things. All right. So thank you, Abubakar. I hope this helps. So as part of the solutions for QM for Windows, we are provided the cost per unit, how much it will cost to transport each unit to a station. And then we are also given the total cost. The total cost will be what? Total shipment times what? Cost per unit. That will give us the total cost for each of the destination pair. So it means that from Kansas City to Cincinnati, total shipment is 150 and it will cost 1,500 with a cost per unit of $10. From Omaha to Chicago, we are shipping 25 tons, each costing $7 to transport, giving a total shipment cost of what? 175. So you should be able to interpret the resource or speak to the resource as I am doing here. Yeah. Now you can also do some sensitivity analysis, where, for instance, you change the cost. So, for instance, suppose the cost from Des Moines to St. Louis changes from $5 to $7. So we can solve the problem, taking into consideration that there's a change in what the cost. Then also we can have a situation where here there's a change in demand. Demand in Cincinnati increased to 350. So look at it here, 350. It was 300, now it's 350. That gives us a new solution, okay, so that we can know how sensitive our solution is to changes in cost and changes in demand. Now let's look at a transshipment problem. Now, so if you look at this lecture and this particular slide, we're basically extending the transportation model. So this is a transshipment model, which is an extension of the transportation model. And in this particular case, there is an intermediate transshipment point between the sources and the destinations. So look at this diagram. The S's are the sources, the T's are the transshipment, and then D's are destinations. Now, so you can have in a transshipment problem, items may be transported from sources through transshipment to destinations. So we can move from S1 just a minute. We can move from S1 to T1, that transshipment point 1, before we move to destination 1. We can also move from source 1 to transshipment 2, and then to what? Destination. We can also move from one transshipment point to the other, or we can move direct from the source to destination. And we can move from one source also to the other, depending on the nature of the problem. So those are the characteristics of a transshipment problem. So let's modify our grain elevator problem to include transshipment. So here we are adding the farms from which the products are transported. So we have Nebraska and Colorado. These are then now the sources. Okay, so we have two sources of the grains, Nebraska and then Colorado. So from the farms, we transport the items to the grain elevators. Okay. Then from the grain elevators, we now transport to what? The mills, which are Chicago, St. Louis, and what? Cincinnati. So which means that we have three main points. First is the farm, which is the source. And then second, we have the transshipment, which is the grain elevator station or stations. And then we then have thirdly, the destinations, which are the mills. Okay. So you can look at the network of transshipment routes here. So Nebraska farm has 300 production capacity. Colorado also 300. So we can shift from the farms, from each farm to each elevator station for storage. Then if we are ready to mill, we can then now move it from each of the elevator stations to the mills. So you will see that this is a network of transshipment where goods are moved from the source, here farms, to storage facilities, which are transshipments, and then finally to the mills, which are processing plants and are basically called destinations in these models. So you would find that when we now introduce transshipment, our modeling framework will change. So in terms of the minimizing part, we have to minimize the costs of transporting from the farms to the transshipment stations and from the transshipment stations to the destinations. So that is why you see now that the minimization problem is longer. Because first, we have to shift from, so let me come here, maybe you get it clearly. So we have modified the numbering so that you can get it more clearly. So we have now decided to number them 1, 2, 3, 4, 5. So the farms are numbered 1, 2. The elevators are numbered 3, 4, 5. Then the destinations are numbered 6, 7, 8. Okay. So from the previous problem, we are just adding shipment from the farms to what? The elevators. So this one will be what? X1 3, X1 4, X1 5. This will be what? X2 3, X2 4, X2 what? 5. So those have been now added to what we had. So 16 X1 3, which will be the cost of what? Shipping from what? From 1 to what? Transshipment. The first transshipment, which is number 3. So this will down be from farm 1 to what? The second transshipment, which is number 4. This will then be movement from farm 1 to what? Transshipment 3, which is number 5. Okay. Then you now move to what? Movement from farm 2 to what? Transshipment. The first transshipment, which is number 3. Movement from farm 2 to what? The second transshipment. Movement from farm 2 to the third transshipment. Then you now have these ones. The remaining are movement from the transshipment station to the destinations. Okay, so for this one, for instance, movement from what? Transshipment, the first transshipment to what? The first destination. And if you look at the numbering, the first transshipment is numbered 3 as a subscript. And the first destination is numbered 6. So here you now move from what? The first transshipment to the second destination, first transshipment to the third destination. Here, second transshipment to first destination, second transshipment to second destination, second transshipment point to what? The third destination. Then third transshipment to first destination, third transshipment to second destination, third transshipment to what? The final destination, which is the third destination. Okay. Now, so in terms of the constraints, we have quite a number of them because we have 3 points. So we now have to get the constraints for the farm, and then the constraints also for what? The transshipments. And then also finally to the destinations. So let's look at how it works. So first is from the farm. So let's go back to the diagram. So the first one is that, first constraint is that what can be supplied from Nebraska to Kansas and then to Omaha and then to Des Moines should be equal to 300. And that is this one. Then what can be supplied from Colorado to Kansas, to Omaha, and then to Des Moines should also be equal to 300, which is this one, the second constraint. Now, Then, in terms of the demand, we can then look at the constraints that I am trying to put together. We're saying that the total amounts that we can demand from the transshipment stations, for instance, for the first one should be equal to 300 from here. So, for instance, total amounts that can be demanded from Cincinnati from these sources, that's the transshipment points, should be equal to 300. And the total amount that can be demanded from St. Louis, from Omaha, Kansas City, and then St. Louis should be equal to 100. So those ones are what we are illustrating here. Okay. Total amount that can be demanded from Chicago to Chicago, from Kansas, and then Omaha, and then there's more. It should be equal to 300, 200. So that is this one. So those are the demand constraints. Now we are left with what we call the transshipment constraints. And the transshipment constraints basically is that we come here. So let me delete the ink so that I can illustrate it well. So these are the transshipment points. The constraint is that the total amount that is transported to each transshipment point should be equal to the total amount that is taken out of those same or that same transshipment to the destination. I take it again. Total amounts transported from farms to each transshipment point should be equal to the total amount that is sent from each transshipment point to destination. And that is what you see here. So for instance, let's take the first transshipment constraint. Let's look at this very carefully. What we are saying is that the total amount that is taken from, so let's look at it from here. The total amount that is brought from Kansas City, from Nebraska to Kansas City, plus the amount that is brought from Colorado to Kansas City. So that is what is here. These two items. This one is X113. X113 is the amount transported from Nebraska to Kansas City, plus X23. X23 is the total amount transported from Colorado to Kansas City. So we are saying that whatever is supplied to Kansas City should not exceed what it can send out. So what it can send out from Kansas City, we can send to 3 destinations labeled so X36 is amount that is moved from what? Kansas City to the first destination. X37 is the amount moved from Kansas City to the second destination. And X38 is the total amount that is taken from Kansas City to the last destination, which is one of the mills. Okay. So therefore, the total amount that is supplied, okay, let me delete and illustrate it better. The total amount that is supplied is to the mill, and here we are talking about the first mill. Sorry, I'm talking of the total amount that is supplied to the transshipment point. So the first transshipment point should not be more than the total amount we take from that transshipment point to the mills, which are Chicago, St. Louis, and then Cincinnati mills. So we then say that whatever the exact amount that comes to a station is the exact amount that goes out of the station. So that becomes the transshipment constraint. So therefore, yes, we are saying that the total amount that is supplied to the transshipment point is equal to the amount that is transported from the transshipment point to the destinations. So that is what these constraints are about. We call them the transshipment constraints. Okay. So if you open Exhibit 6.11, you would see the problem set up in this manner. So it is similar to what we did for the transportation problem, just that we have added a portion for the transshipment. Okay. So we have to add from the farms to the elevator and from the elevator stations to what? To the mills. Okay. So then we include the cost of each of these points. And that we can solve it. So if you open, let me see whether I can get it. So basically the setup is the same as the transportation problem, 6.11. Just that in this particular case, we are adding a transshipment point. Okay, so if you open Exhibit 6.11, this is what will show up. So put your cursor in the cost column, and we see that we have double sum product here. Because we have to do sum product for the farm to grain elevator stations and from grain elevator station to the mills. Okay, so that's why we have double sum product in this particular case. So you can go to data, and then you see the constraints. So you have the demand constraint, the supply constraint, and then the transshipment constraint. We still use the simplex method. You solve, and then this is the solution to the problem. Wait a minute. Okay, this is a solution to the problem. So the total cost will be $12,400. And then the solution tells us that from Kansas City, nothing is shipped. Omaha, we have 300 being shipped to Cincinnati. And then from Des Moines, we have 200 being shipped directly to Chicago. Okay. So the transshipment problem is just some upgrade to the transportation problem. And the solution process is basically the same. So this is the solution tree, which tells us how the flows move from one point to the other. Okay, so you can look at it later on. So finally, let's close with an assignment problem. Okay. Now, in an assignment problem, we are dealing with a situation where the supply at each source and demand at each destination will be limited to 1 unit. Supply at each source and demand at each destination is limited to 1 unit. So that's why we say that it's a special form of a linear programming problem. And here again, we can have a balanced assignment problem or an unbalanced assignment problem. In a balanced model, supply and demand are equal. In an unbalanced problem, supply and demand are not equal. Nabil is asking whether we can solve this using matrix, or you mean matrices. That would be a very hard nut to crack. because you are dealing with several dimensions of a matrix. It will rather become a very complicated situation. So it will be better we use the computer approach. That's what I would advise. We don't need to look for hard solutions when some simple solutions are available. Now, so let's look at an example here where we are supposed to assign 4 teams of officials to 4 games in a way that will minimize the total distance traveled by the officials. Supply is always 1 team of officials. Demand is always 1 team of officials at each game. So here you are dealing with, for instance, a basketball league where you have a team of officials that are scattered across the country. And you want to allocate these team members to different game sites. And there are variations in the distance covered in miles. So in this particular case, you have officials A, B, C, D. Then the game sites are Raleigh, Atlanta, Durham, and then Clemson. Now, what you are asked to do is to assign these officials to the game sites such that the distance covered is minimized. So for team A, if you assign them to Raleigh, cover 210 miles, but to Atlanta, they will cover 90 miles. To Durham, they will cover 180 miles. And to Clemson, they will cover 160 miles. Okay? So how do you assign these officials to the game sites such that cost is kept to the best minimum? So let's look at how this is solved. So we set up the objective function. Here we are using the initials of the game sites as the subscripts. And then the officials, we use the A, B, C, D tags. So our objective function will be to minimize the distance covered. So we are minimizing the values on the table here. So take note. So this cell will be what? XAR. So 210 times XAR plus 90 times what? XAA plus 180 times what? XAD plus 160 times XAD, and so on and so forth. So that is what you have here. You do that until the end. So that's the objective function. Now, it is subject to a constraint that we can only allocate one team member each supply source can only produce one team member, and each demand side can only receive one team member. So that's why we said that the sources and then the destinations can only receive one team at a time. So you can get that from here. Just to give you an illustration so that you can set up a problem on your own. So we are saying that if you take the first group of officials, the allocation to Raleigh, Atlanta, Durham, and then Clemson should be 1. So that is the first one. That is this one. Then the second one. Allocation to Raleigh, Clemson, Atlanta, Clemson from Team B can only be 1. In other words, Team B can only be allocated to only one of the venues. Team C can also be allocated to only one of the venues, the same as D. So that will give you the supply side. Then you now come to the demand side. The demand side tells you that each game site can only receive one team member. So it goes the other way. So let you get it there. So it means that Raleigh can only receive one team from these sources, from one of teams A, B, and C, and D. One of teams A, B, C, and D. So that is this one. Then Atlanta also can only receive one from A, B, C, up to D. Which is the second demand constraint. Durham can only receive one of the teams. Clemson can also receive only one of the teams. So that completes the demand side. So that then gives us the final constraint we say is what? The non-negativity constraint. Okay. So you just need to understand for the assignment model, transportation model, and transshipment model, what I want you to understand is, first of all, how to set up the model. So set up the minimization model, set up the constraint functions, and then use the computer to solve it. Then when you have used the computer to solve it, then you interpret it. So in the exam, if a transportation assignment or transshipment problem is going to come, I may ask you to set up the model, in other words, the minimization problem, and then the constraint function, but you will not solve it in the exam. Then I can provide the solution and ask you to interpret the problem. So that is all that I expect from you in this section. But I'll give you assignment where you use a computer to solve it. Okay. But in the exam, if a problem of this nature is coming, all you need to do is to know how to set up the minimization problem, the constraint functions as well, and then be able to interpret the resource. So this is how we set up the problem. So you ensure that, so you see that we have 4 teams. The teams available is restricted to 1. Then we have also indicated the mileage. And the solution. So if you have shared the exhibit with you, 6.15. So this will be the solution. The solution tells us that let team A go to Atlanta. Assign team C to Durham. Assign team D to Clemson. And they will travel 450 miles, which will minimize the time traveled or the distance traveled by these individuals. So this is a map of the solution. So let team A go to Atlanta, team B goes to Raleigh, team C goes to Durham, and team D goes to what? Clemson. If you use QM for Windows, and I've shared with you exhibit 6.18, this is how it will solve it. The portions that are marked blue are the assigned solutions, and it gives you the miles that they will cover. So if you sum up the miles that are in blue, the max in blue, it should lead to the 450, which is the optimal solution, 450 miles. So team A assigned to what? Atlanta, which is, and it will cover 90 miles. Team B assigned to Raleigh, and this team will cover 100 miles. Team C assigned to Durham, and they will cover 140 miles. And then team D, assigned to Clemson, and the mileage will be 120. So if you want to replicate this result, use exhibit 6.17, which I shared with you, okay? So this is another example which I provided, where, for instance, concrete is transported from supply points to demand points. Okay, so here, you have to determine whether demand is equal to supply. And you see here that this is an unbalanced problem. The demand and the supply are not equal. Sum them up, and you see that they are not equal. So, which means that the constraints will contain inequalities. So this will be 280. And then 320. So you see that demand is greater than supply. So in this case, you will see the solution involves inequality constraints, because demand is not equal to supply. Okay. So then you see that some of the stations will not get what they demand. So for instance, construction site B demands 70, but it will get what? 30, due to the fact that demand outstrips supply, and it will cost 2,830. Okay, so that is how you deal with transportation, transshipment, and assignment problems. Okay. All right. So on this note, we've come to the end of the lecture. I guess you have posted all your questions, but if there's any question, you can post it on the chat in the next few minutes. But in terms of the lecture, I think we are done with the lecture. God willing, next week we'll move to a different topic, which is likely to be our final lecture for the course. So between today and tomorrow, I'll give you a group assignment. So you are to use your usual groups to handle that assignment. And it will be based mainly on this particular lecture that I have delivered. I've shared the textbook with you, so you can read chapter 6 to get an enhanced understanding of this very summarized presentation that we have had. Okay, so Francis, it's not possible to recap last week's lecture, as we are moving into a different section for other lectures to take over. Next lectures, the next set of lectures are supposed to take off from 10:30. So that one is not possible for us to do that. I would advise that you read chapter 5, right, of the book, Integer Programming. Read chapter 5 of the book, or you go to our YouTube channel and then you look at the previous recording on integer programming, and that should be adequate for you. Okay. All right. So on this note, I thank you very much for participating in the lecture. Continue to read about management science, and we hope that at the end of the day, we'll fully achieve our objectives. So thank you very much.